All right, Dr. Lane. This is my reassessment on the momentum principle, or better, conservation of momentum. And this is number 23 on page 263 in the book. And it is asking, what is the recoil of the rifle? Now I'm given the mass of the rifle, the mass of the bullet, and then the velocity of the bullet, but not the velocity of the rifle, obviously. So momentum, obviously, mass times velocity. So the momentum of the bullet is going to be its weight times its velocity, which gives me that. And the momentum of the bullet is equal to the momentum of the rifle, and I'm about to prove it thusly. So you set those equal to each other, and then that gives you the momentum of the bullet on the left side, and then of what we know, all the knowns and the unknowns that we have of the rifle on the right. And we're trying to find this. So we divide it by 4.5 each side to give us our velocity, which comes out to 1.82 meters per second. Kilograms cancel out. And that's all it's asking for is a recoil of the rifle in the opposite direction of the bullet. Now, I want to step further just to find out the momentum of it, because all you got to do is just plug this into the actual equation of the mass times the velocity. That gives me 8.19 kilogram meters per second. So to go another way further, in this equation, I went ahead and said that Thor was just doesn't like Hyundais. We'll go ahead and say that. And he throws a Craftsman hammer at it at first at a velocity of 400 meters per second at a 1,800 kilogram car. Kind of light, probably a Hyundai, some sort of import. He doesn't like imports. And then want to find out how fast the car flies back. At what velocity does the car fly back? Very similar to that other one. But I'm going to do it with a regular Craftsman hammer, and then I'm going to do it with Mjolnir to establish that the momentum is conserved from the hammer to the vehicle in both cases. So the momentum of the Craftsman is its mass times the velocity at which it is thrown, 400 meters per second at 20 kilograms. So that gives it 8,000 kilograms meter per second. These two equal each other, or at least very close to. So you set them equal to each other, same as the last problem, and then plug in my knowns that I do have, which is the mass of the car. Don't know the velocity. So I divide each side by, and that gives me the velocity of the car at 4.44 meters per second. And that's how fast the car is going to fly back whenever the Craftsman's thrown in it. Now, I plug it in to the momentum of the car equation to get its actual momentum, and it's 7,992 compared to the hammer when it's thrown, the momentum of the hammer at 8,000. So those are relatively close because this one weighs like 20 kilograms and this one outweighs it by so much. So the fact that they're both very close to each other as far as momentum, then that rings truth. Now we did Mjolnir. Now, I was ultimately told that it does weigh as much as a neutron star, which they have a bunch of givens. It could be 2.5 times 10 to the 30 or 5.2 times 10 to the 20th. So I just went with this one since I already worked it out, even though it was made from a neutron star from the Dwarven Blacksmiths, which was commissioned by his father Odin. So you plug that in, and that gives us the momentum of Mjolnir whenever it is thrown, 1 times 10 to the 33rd kilograms meter per second. Then you set that equal to the car, which gives us the car flies back at a velocity of 5.55 times, very large number. Thing is moving. Why it's not turned to dust, I don't know why. But then I plug that back in to find the momentum of the car instead of just the velocity, and that gives me something quite similar to the momentum of the hammer, proving thus that momentum is conserved. Alrighty. And thank you for not changing everything on Wikipedia about the Thor hammer. All right, bye.